Morning, everybody. Fair warning, a quiz is going to come up in about 30 seconds. But we were talking about electric potential and this kind of weird idea about how the electric potential can be a map for us of what the electric field looks like. And so we're on our way to trying to figure out how electrical circuits work. We're going to really start diving in today about electrical circuits. But I ran out of time last time to do a quiz for what these potentials, equipotentials, and how you can read them, right, as to what's going on. So just by way of review before the quiz. Electric fields and lines of equal potential share, well, they're always what to each other? They're always perpendicular, right? Okay? So if you can read one, you can more or less read the other, right? I guess is what I'm trying to convey here. So let's what are these? Okay, top one's an EEG. Okay, don't ask me to say what those words are. Electroencephalocardiogram, something, blah, blah, blah. Brainwaves. Okay, that person is wearing a very funny hat. That hat, I mean, my vector hat looks better than that, doesn't it? Each one of those wires is leading to a sensor that the skull cap, right, is reading different electrical signals or different parts of the brain. Okay? Your brain has lots of potentials going on in it. What's the bottom one?
That's not so good.
This is the EKG, right? Am I getting these things right, anatomy and physiology students? The electrocardiogram, is that right? No.
Because it's K.
Yeah, but what's the K?
It's just from German. It's electrocardiogram.
It's electrocardiogram, right? Okay, right, okay. Which is the electrical signal that your heart puts out, right? So by studying these voltages and how they vary in time, one can make predictions about heart health, brain function, all that kind of stuff. Recently, it was a woman who had lost her voice due to, I don't know what the root cause was. If it was stroke or an accident or paralysis or something like that. But researchers connected her brain via a voltage monitor, more sophisticated than that, but it measured voltages, and then wired those impulses to ChatGPT to give her voice back. So all she has to do is think the words, and the computer can speak for her. We are living in Star Trek. Like, seriously, it's absolutely incredible. And what I've been teaching you, right? All of this Coulomb's law, all of this electric field, all of these electric potentials, this is where this ends up, right? Now, these things are incredibly complicated to understand and take years and years of training to be able to piece apart. But they can be boiled down to a device in a doctor's office for being able to measure and diagnose, right? It always astounds me where these fundamental principles come, right? You're like, well, Mr. Mayor, why did you start here? This is what I'm interested in. I know, but this is really hard, right? And I just want to, as a carrot on a stick, right, tell you that this is kind of like where we're going, right? If you understand the basics, then someday you might be able to understand how some of this works. So what we're going to do now is we are going to move towards very physical objects that take advantage of our understanding of Coulomb's law, electric fields, and electric potentials. These very physical things are circuit elements. They are the pieces and parts that make up the technology that we use and rely on every single day. From your cell phone, your computer, to your televisions, to the internet, everything. They're based on these principles of electrical circuits. And so we're going to talk about, like today we're talking about capacitors and resistors. And then next week we're going to move into like circuit analysis, right? Understanding electrical circuits with series and parallel and all these different kinds of things mean. So let's start with a device called a capacitor. Now, just from the name, what does it sound like? Like capacity, right? So a capacitor fundamentally is storing something, okay? And don't confuse it with a battery. I mean, even though, look at these things. They look battery-like, don't they? Okay? It turns out a cylinder is a really easy shape to deal with in terms of making things stable, like mechanically stable, and also in terms of like packaging. Cubes and rectangles would be better, but manufacturing-wise, these are easier. But a capacitor stores electrical charge. That's what it does. Now, you might be thinking, but Mr. Balogh, isn't that what a battery does? No. So right here, we've got to clear something up. Even before I get to batteries, I'm not going to talk about batteries till later. A battery does not store electrical charge. Even though when you want to give your phone more juice, you say that you are going to charge your phone. This is part of what makes my job so hard, right? I have to teach you things that you thought you knew were true and say, no, they're wrong, and you fight me the whole time, right? I mean, you don't right? But your brain is going, oh, no, it's stupid, right? You never charge a battery up. So you charge a capacitor up. Capacitors, charge goes in and out. So if a capacitor stores charge, what does a battery store? Yeah, that's what I thought. It stores potential. We'll get there. We'll get there. Let's back up and talk about what a capacitor is, okay? So this is not how they're actually made, okay? But you could think of a capacitor as a chunk of conductor, just whatever shape it is, and another chunk of conductor. So two conductors, okay? They start off neutral, but then we're going to put charge on them. And we're going to put positive Q on one and negative Q on the other. The charge on both of these conductors is exactly the same amount, different opposite signs. So you tell me what's going to happen. If I have excess positive charge on that one and excess negative charge on the other, what forms or exists between those two conductors? There's a voltage. There's an electric field. Is there a force? Yeah, right? Opposites attract. Okay, so we nail it down so it can't move, right? So we're not going to let the force happen. But since forces are there, that means electric field has to be there. Where's the electric field start? On the positive and goes to the negative, right? And is shaped however it's shaped, okay? Which means that there are lines of equal potential that exist. So we've got force, we've got electric field, we've got potential. Golly, a capacitor is hitting all three of the major highlights of the first part of this semester, isn't it? And so we tried to figure out, okay, the question becomes, is there a relationship between charge and voltage? What do you think? What's your guess? Yes, there's a relationship. What does that relationship look like? What happens if we increase the charge on both of those conductors? Do you think the voltage go up or down? Go up? It makes sense, right? More charge means more force, means more electric field. More electric field means voltage changing faster, right? steeper mountains and valleys and all, right? Okay. So it seems like there should be a direct relationship between these things, right? But is charge voltage? No. Charge is coulombs. It's a fundamental thing that makes up all matter in the universe. Voltage is electric potential, which is like a step removed from electric potential energy, but it's pretty close. So one's in coulombs, one's in volts. Those are not the same unit. So we're not allowed to draw an equal sign, right? Unless we do what? We put in a constant. This is a trick that physicists do all the time. Oh, they're not the same thing? Well, we'll set them equal anyway and just put a constant in and hope that the constant comes out constant. Okay? The constant that we drop in there is called the capacitance. The device, the physical device, that literally consists of two conductors, okay, separated from each other, okay, is called a capacitor. Usually, a capacitor is made from what we call parallel plates. This was a very lame attempt at drawing two vertical plates in 3 dimensions next to each other. Okay? If we were to look at this from like face on, we'd have one plate there, one plate there. We'd charge one plate up to be positive, say that one right there. Okay? And then we charge the other one up to be negative, say that one right there. Okay? And then you can electrically like connect them through a wire. But inside of a capacitor, you will have electric field as long as there's charge on the plates. Notice the charge on a capacitor is the magnitude of the charge on one of the plates. Like, what's the net charge on that capacitor? It's 0, right? Okay. But what we've done is we've taken what would be neutral and separated it out. Okay. And to maintain that separation, we have to apply an electric potential. And so a capacitor will literally be charged up. When you connect it to an electrical circuit, like a battery or anything else, the battery will push charges not out of it, but through the electrical circuit and dump them on the plates, storing energy, real energy like joules, in the electric field between the plates. And you now have something that can store electrical charge. What can you do with that? Why would you want to store electrical charge in the first place? I mean, like, what's the point? No? How well does your phone work on 0 battery? Doesn't, right? Where does your phone get its energy from? The battery, right? Which is kind of a lie. We're talking about doing electrical work here. Just like you fill your car up with gasoline in order to make it go, right? The car is a mechanism for converting chemical potential energy into kinetic energy. Electrical circuits are the vehicle for changing electrical potential energy into some sort of work. Whether that be the display on your screen, the video game you're playing, the internet thing you're looking up, whatever's going on, the light bulb that's turned on, whatever it is, right? Electrical work is happening. And so what we're trying to do is capture that. So now we've got a device that can take that charge, store it up, like I can charge the capacitor up, and I use the correct terminology there. I can charge the capacitor up, disconnect it from whatever I charged it with, take it somewhere else, and then use that charge, use that potential to do work. So I ask you again, what sorts of devices need to be charged up and have electrical work done? Now you'll notice, unlike a battery, a capacitor can kind of go up and then get dumped. And then it'll go up and then get dumped. It's not like a continuous source, depending on the type of circuit that you have, okay? I want to show you a video of what happens when you try to discharge a capacitor too fast. Does that poor graduate student look like he is scared for his life, or I actually have a bank of these in the back that I'm gonna show you in Unit 2. I think I've referenced this device before, so one that I'm afraid is gonna kill me. This is why.
Large capacitors may look innocent, but they can be very dangerous when they're charged. This bank of 4 capacitors in parallel will be charged to 400 volts.
Doesn't sound like a whole lot, right?
The capacitors are now fully charged, and we will disconnect them from the voltage source.
See how careful he's being?
Though they look benign, these capacitors are now storing a lethal charge.
Okay, you can't hear it, but that was a very loud sound. Look at the scorch marks on the bar. It's basically got a spot welder right there, okay? Capacitors, large capacitors, can be very, small capacitors can be very dangerous. I used to work in an electronics repair shop in college, and I remember we would interview new hirees, and we would say, okay, here's a broken television, we would like you to measure the voltage on the back of the television. And we would watch them as they grabbed their probes to do the measurement, and then we would tell them when they died. And of course, it was totally inert, it was totally safe, right? We weren't exposing them to anything. But just by watching what they touched with what, we could tell them at the end of their interview they were alive or dead or not. And that's because old televisions used to be able to store lethal amounts of charge in their capacitors for years after it was unplugged. Okay? So capacitors can be very dangerous, but they can be very useful because there are certain situations. So the thing a capacitor has over a battery is a battery can push charge places and it can do it for a long period of time. It just tends to do it very slowly. A capacitor can push charge very fast, but then it's done. Can you think of any applications where you would want a lot of electricity really fast?
Jump a car.
Jump a car
For the little
and jump a
person.
heart. Yeah, jumping a car is exactly right. Okay. Jumping a heart. What's that person doing? This is an ancient device called a camera. Okay, right? And in the old days, cameras had flashes on them. I know modern phones have flashes, but it's a lie. It's a bright LED. Okay? But cameras used to charge up their flashes, okay? And you'd have to wait. Think about that. You'd have to wait for the flash to be ready. What was the battery in the camera doing? Charging up the capacitor. And then the capacitor would just charge very quickly through the bulb to make that really bright light, synchronized with what the shutter was doing. We'll get into cameras when we get into optics, okay? And I know, you're so old using a camera. They're still used, okay, quite a lot. The thing over there on the right-hand side is a defibrillator. What does it do? It defibrillates. What's fibrillation? It's what? Okay, it's when the heart is beating irregularly. It is actually the most dangerous condition that the heart can be in. I'm speaking in terms of emergency medicine, okay? Somebody who's having a heart attack, that can mean several different things, okay? The most dangerous being that their heart is still beating, but it's not beating properly. If a heart is stopped, we can fix that or not fix that, okay? But when a heart is beating irregularly, okay, it can actually fight against life-saving techniques, okay? And so, a defibrillator's job is to stop that irregular heart rhythm. How do you stop a heart that's beating irregularly? You punch it, okay? And not with your fist. You give it an electrical shock. Because it's an electrical series of voltage changes through the heart muscle that give rise to that standard lub-dub, 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 that, unless somebody you're interested walks by, lub-dub, 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 right? Okay? But a heart that's in fibrillation is doing lub, 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 lub. It's like a misfiring engine. It's just not pushing blood anywhere. It's typically fighting against itself, and no amount of CPR is going to fix it because it's an electrical problem. And so a defibrillator, and you medical dramas, right? Okay, clear. Okay. Why do they want everybody to stand clear? We're shocking a body, right? And if you're touching said body when you are now part of the circuit. And it's not very pleasant, it hurts, okay? Don't ask me how I know. You shock, and usually the first shock stops the heart. Key point of information, follow up the first shock with another one, okay, right? Like, okay, because usually you're gonna stop the heart, and then you're gonna start the heart. Why are they rubbing the paddles? There's gel on the paddles, okay? There's an electrical conductive gel, okay? Because skin naturally is not terribly conducting. It depends on how much oil and grease and water and all kinds of stuff. Human skin grows, right? But you gotta rub the gel and spread it across the paddles, okay? Put it down. Big units like this, I haven't seen in a long time, even in an emergency room. They're getting smaller and smaller, and they're moving more and more toward the stick-on single-use pads. And even nowadays in public places, you'll see things that are called AEDs. They'll be probably right next to where the fire extinguishers are, right? Let's say AED. That is an automated external defibrillator, okay? Basically, it's Siri connected to one of those, okay? And, or Google Lady, or whatever your favorite disembodied computer voice is. Right? Basically, if somebody's having a heart attack, you can bust one of these out. You don't need to know anything. Literally, you open the zipper and it starts talking at you. It'll say, remove the victim's clothing, put the pad here, it'll be like a little picture, and then it'll say, okay, stand back. And it's just gonna read their heart rhythm. And the device will determine whether or not it needs to apply a shock. What kind of shock? Not just a big boom, but like, does it need a little more finesse to keep that heart? And AEDs take a person's survival chance from like 5 to 8%, all the way up to 70 to 90% if they're having a cardiac problem. Like literally, doing CPR doesn't work to restart a heart. What is CPR for? To keep their body from dying, to keep their brains from dying until one of these can show up. Either in an ambulance or AED or something like that, okay? I'm not saying don't do CPR. Yes, do CPR, especially if you're trained in it, right? But a friend of mine, EMT for 20 years, never once had to do CPR on a person until 1 week he had to do it twice. Both people died. Like it's CPR doesn't save lives, okay? It maintains life for a little bit of time. And then if you don't fix the problem, you're in for a heartache. But AEDs are absolutely incredible for changing. I mean, there's one on every plane now, and it just changes the survival rate for somebody that has a heart attack on a plane, right? You can wait 45 minutes to an hour to land that plane safely and get that person to a hospital. So it's incredible technology. All right, so let's go back. Where did it go? Let's go back to this, right? So in general, a capacitor's voltage and charge are related to each other through this constant called the capacitance. Capacitance depends on, well, two things, okay? It's got an epsilon naught in it. So what do you automatically know? Do you remember? Epsilon naught was a clue. for something being there. Put you out of your misery. It was a clue that the electric field is lurking somewhere. Okay? So epsilon naught is a constant, 8.85 times 10 to the minus 12. Capital A is the area. The area of the plate. So this is the capacitance of a parallel plate capacitor. And if you've ever opened anything electronic, you'll know that there aren't just two big plates sitting in there, right? Those circular, those round cylindrical ones that I showed you are actually parallel plate capacitors. It's a piece of conductor, and then there's a thin layer of plastic and another conducting sheet, like aluminum foil type stuff, okay? And then that parallel plate that's held in place by the plastic insulator to keep them isolated from each other, that gets rolled up, okay, in like a burrito, okay? So even though it looks like a cylinder, it's really a flat shape. It's a parallel plate shape. So how do we get more capacity? How do we get more capacitance on our capacitor? Increase what? Area. We can make the amount of material bigger, right? That D right there is the separation distance between the plates. And so what does that tell you about storing charge? What happens as the distance between the plates gets smaller? Note that it's in the denominator. It increases the capacity for the capacitor to store charge. But wait, we're getting these charges closer together, aren't we? We're getting them closer together. And what do positive and negative charges want to do? They want to get closer together. So we can actually kind of like almost neutralize charges that are close enough together, which means there's more room for charge to pile onto the plates. So we can take advantage of this rule, this idea that capacitance is a function of the physical parameters of the object, the area of the plates, and the distance between them, to change how much charge we can put into things. And so what I'd like to do right now is another quiz. Seeing if you can tease out the relationships between all these things. To do that, we need to move on to chapter 20. And this is where we get to talk about what batteries really do. So we've talked about voltage now, and voltage is electric potential and is related to electric potential energy. What we want to be able to do is harness that energy to be able to do work. And that usually means changing potential energy into kinetic energy, right? But in an electrical sense, what does that kinetic energy take the form of? It takes the form of charges moving along circuit pathways or along wires. So we are transitioning now from electrostatics, where the charges haven't really been moving, like we charge up a conductor and leave it be and do something, right? We're moving now into electrodynamics, where again, charge is starting to move. So the bad news is that I use the word dynamic. So what does that mean? It means harder, right? Because we did dynamics as unit 2 in physics 2A. We went from kinematics to dynamics, right? And free body diagram and the whole that thing, right? The good news for you is we're not immediately going to jump that deep into dynamics. We're going to save that for unit 2. Okay? We're going to keep dynamics simple for the beginning, okay? And develop everything we know about DC circuits. And then we're going to get back into the real meat of electrodynamics and what happens when charges really start moving places and all the magic that happens there. So, what's current? Like, where have you heard that word before? Water current, right? Okay, a current in a river. What does the current describe? flow. Okay, usually there's a direction associated with it, right? Downhill or downriver or whatever, right? Okay. But to measure the current in a river, what would you have to know? How fast it's going? How much of it is there, right? You can have a small stream that's flowing fast, but it may not have as much current as, say, the Mississippi that moves slower, right? So there's something about amount of water that's flowing in the river that seems to be important. So current is how much charge is flowing through a conductor per second. Don't spell words. Q per time. And really, it's a change, right? We're counting charge. So if we've got like if we've got a wire, here's a wire, okay? And it's got like a cross-sectional area, it's like a cylindrical wire, okay? We can say, okay, if we count, several charges moving down that wire, okay, per time, we'll call that the current. So it's a charge per second, which means that it's a coulomb per second, otherwise known as an amp, which is short for ampere, or if you're on the other side of the Atlantic, ampere, right? Okay. So 1 amp is 1 coulomb every second. This measure of how much charge is going place, charge per time, is really more critical than some of the other measurements that we've had prior to this point. I mean, voltage is important. They're all related, as you're about to see. But when it comes to your safety and the ability for electronics to do work, it's really current that determines either how dangerous it is or how much work can be done. So this brings up batteries and their voltages and how this affects current and all that kind of stuff. And you see a term up there at the top called EMF. You're going to see this term dropped all over the place in books, online, videos, all this sort of stuff. For you, EMF is exactly the same as voltage. It's got a really unfortunate name. It stands for electromotive force. Yes, EMF, electromotive force. What are the units of electromotive force? Voltage. The units of EMF are volts. And yet it's called the electromotive force. This is a name that comes out of history. Before they understood that charge even existed, like electrons and protons and all that kind of stuff, they were playing around with voltages and currents and all this kind of stuff. And they needed a way to explain, this is before Coulomb's law, this is before all that, they needed a way to explain why it seemed like there was something flowing through a conductor. Again, they didn't really know what the something was. They actually literally thought that conductors were full of fluid, right? That they just couldn't see, right? And so they talked about the electromotive force that would cause the electrical fluid to flow, that would then cause the spark to happen or whatever, okay? It would only be later that we would realize that they were partially right but mostly wrong. Is there a force acting on a charge if it's being pushed somewhere? Yes, it's called Coulomb's law, right? But the measure, the thing that you're measuring, the thing that's causing the current to happen in the first place is the electric potential. The electric potential gives a charge a reason to move. Just like the gravitational potential gives an excuse for this ball to go places, right? Where does the ball get its kinetic energy from? It gets it from the electric potential, or the gravitational potential energy that's in the Earth's magnetic gravitational field. Charges get their motion from the energy that's stored in the electric field. And the energy to store in the electric field can be measured by the electric potential or the voltage. It's all connected. Batteries are sources of EMF. Batteries provide the potential energy for charges to go places. Batteries do not store charge. They can't. I don't care what your chemistry teachers say about it, they do not store charge. Where does a battery get the charge it tries to push? Where do the electrons come from that light up light bulbs and make your phone go and all of that kind of stuff? The redox reaction that's taking place with a battery is, you know the word I wanted to use right there, is not, it's moving charges around. It's not sending charges out of the battery. It's causing a rearrangement of electric potentials. Where do the electrons come from in an electrical circuit? It's too obvious.
Circuit itself?
The circuit itself. The electrons come from the conductors that are in the wires of the circuit in the first place. Just because a conductor neutral doesn't mean it doesn't have charge in it, right? It just means it has equal amounts of positive and negative charge. And so a battery it pumps, it pushes, it gives electric potential to the charges that are already there to go in a certain direction. Right? The Earth, you don't need to give it a mass, right, for it to be able to do something. The mass is already there, right? The masses that experience the Earth's gravitational force are just already there, right? Same thing in an electrical circuit. A battery pushes. It doesn't provide charge. It's not a source of charge. Positive charge doesn't come out one end, go all the way around, and then go back into the other end and somehow disappear or magically get changed into a positive charge, right? Okay? That's not what happens. A battery pumps. It pushes. It doesn't charge up. It doesn't discharge. Even though you're about to see me draw a bunch of diagrams where a positive end of a battery has got positive charge coming out of it, right? Positive charge flows out of that end because that's the direction where the high electric potential is. And what do positive charges want to do? They want to roll downhill. They want to get as far away from high potentials as possible, right? So they'll roll downhill through the circuit to get to the negative end of the battery. Okay? So EMF, okay, is a measure of a battery's ability to provide this pump. And it's measured in volts, okay, because it is an electric potential. In truth, a battery consists of a couple of things. It consists of this source of electric potential. Not quite sure how I really want to try to describe this to you, okay? But a battery, here's like the black box that's a battery. It's a mishmash of chemicals inside of here, okay, doing something. We'll leave that black box alone for now, okay? And then it has something called an internal resistance that we haven't talked about resistance yet. As a battery, okay, fine. As a battery discharges, okay, it's not losing charge, it's losing the ability to push. And the reason it's losing the ability to push is it's starting to fight against its own internal resistance to the flow. It's like your car's engine is getting old and it's more and more friction in there. More and more energy goes into turning your car's engine than it goes to going to the car's tires, right? And over time, cars' engines lose horsepower and all this kind of stuff, just because they're getting old and all that kind of stuff. So a battery does that. As those chemical reactions take place, the battery has to work harder and harder against itself until it gets to a point where it can't push against its own internal resistance. So it's trying to push with 1.5 volts of potential, but its own chemistry is fighting with 1.5. And when you go to actually try to use that battery, nothing happens. It's been discharged. So what are you doing when you're recharging a battery? You're reversing those chemical reactions and lowering the internal resistance of the battery so that it can push charge through the circuit again. Let me show you a video of what happens to batteries when they are discharged. And in the video, you're going to see they're going to measure the voltage of 2 batteries without any loads on them. And you're going to see it's the same. But as soon as they try to load or give the battery something to do, you're going to see what the internal resistance of the battery will cause.
These 2 sets of batteries appear identical and show approximately the same reading on a voltmeter, but there is a difference. When a light bulb is connected to this set of batteries, the bulb lights and the voltage of the batteries remains about the same. When we do the same with this set, the bulb fails to light and the voltage of the batteries drops to nearly nothing. This set of batteries has been heavily used and has a high internal resistance.
You notice how they really tried carefully to not say discharged? Right, okay? It's actually, physicists really don't like that term, right? Because it's not what's happening. Oh. Batteries, okay? This is our bucket of used batteries, okay, right? So when we use batteries up, we want to be responsible with the environment, we want to recycle into here, right? Okay? So somebody, and I think they were a chemist, thought that they were going to be cute. And they wrote free of charge. This has been like there since pre-pandemic, right? Okay. I wanted to change the sign, right? Okay. It's not that they're free of charge, right? Charge just comes from the circuit. They've lost their potential. See, yeah, found that. I'll put those back later. I'll let them wonder where the batteries went. All right, let's meditate. Okay, so current, voltage are related to each other, much the same way that charge and voltage are related to each other in a capacitor. Ohm's law is this relationship between the I should be fired. The voltage and the current are related to each other, okay? But they're not the same thing, are they? Is a volt a amp? No. So again, how are we going to fix this? Put a constant in, right? Okay. But don't write it this way. I'm going to change this in a second. Okay. We're going to put a constant called the resistance in here. Okay. But for whatever reason, physicists and electricians and everybody usually write this as V equals IR. I don't know if it's easier to say, but V equals RI just doesn't roll off the tongue. It's easier as V equals IR. R is the constant proportionality between them. And this relationship here is known as Ohm's law. You are going to be sick of this next week. It's just going to be this over and over and over and over again. You're like, well, how bad could it be, Mr. Balogh? It's just 3 things. Hold on. This is Ohm's law. And it's a law because it's just a basic statement of how the universe works. The resistance, right, is this constant of proportionality between voltage and current. In fact, if the resistance goes up, current would go down if the voltage stayed the same. So again, it's telling us like what's proportional to what and all this kind of stuff. So resistance, like capacitance, has a physical measure. That's the Greek letter rho, by the way. It's not density this time. That's the resistivity. It's a number, again, different materials have different constants associated with them, but that's the resistivity, times L over A. So a resistor, a physical resistor, can have a length and a cross-sectional area. The longer you make a resistor, the more resistance it has. The smaller you make its cross-sectional area, the more resistance it has. But you get one guess as to what a resistor does. It resists. But as we know from Star Trek, resistance is futile. No? No. Resistance is voltage divided by current. What does a resistor do? It resists the flow of charge. It is the electrical analog of friction. Resistors are devices and circuits that take electrical potential energy out of the system. They're usually the things doing work. Physicists tend to think of light bulbs and refrigerators and electrical generators in your phone as just like one big resistor, okay? It's being supplied energy and that energy is being turned into something else, whatever it is, okay? And so there's an effective resistance that device has in an electrical circuit. But a true physical resistor, whatever it's made out of, the longer it's made, the more resistance it has. The cross-sectional area, bigger or smaller, determines how much resistance it's going to have. So the units here can get a little squirrely. What are the units of electric potential? It's volts. What are the units of current? Amps or amperes. The units of resistance are ohms. The symbol for an ohm is that symbol right there. That is the Greek letter capital omega. I didn't draw it very well. It looks like a... Nah, it's still not drawing it very well. That was a little bit better. Okay? Greek letter capital omega. Okay? Named after Frederick Ohm, the guy that came up with Ohm's law. And it literally is a volt per amp, if you want to think of it that way. I begged of you last time, and I beg of you again, don't go down the rabbit hole of units. Ohm is a standard SI unit, an amp is a standard SI unit, a volt is a standard SI unit. If you're given milliamps, what are you going to do with milliamps? Change it to amps, right? 10 to the minus 3 amps, right? Okay, milliohms, same thing, right? Change it to ohms, and you'll be safe. But this does beg the question. Yeah, I've got time. What's that? That's an ohm away from ohm. It's an ohmmeter. 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 Ohmmeter.
This is what you said you had time for?
Uh-huh. How long have you been holding on to these? Oh my gosh, you have no idea.
Stove. It's a very good stove. Oh.
Ohm on the range. You're welcome. Have a good weekend. What's due on, what's due? Chapter 18 is due on... Wait a second, we do have time for something else. The tutorial center is closed on Saturdays. They're open on Sundays.
Did you find out if that was actually true.
That is true. Heather Walker told me.
Oh, yeah.
Okay, so I've always made homework due on Saturdays because it was the day after draft, and people had time to go to the tutorial center on Saturdays and get to finish stuff up. With that gone, I'm now wondering if we need to change the due day for homework. I'm not going to ask you to decide right now, and we're not going to vote on it, right? But I need feedback. I need you to tell me sometime within the next few days, Friday due dates or Sunday due dates. Okay? It might seem obvious at first, but realize every test week, homework is due when? On Wednesdays, right? So think about, it seems kind of obvious, we'll just push it back another day, Mr. Bailiff, but it really starts to crunch that last chapter right before an exam, right? So think about, do you need the discipline to have it be done on Fridays, right? The same day grass happens? Or do you need that wiggle room? I'm sure I'm gonna get split right up the middle, okay, right, okay? But if you have, think about your life, your situation, how would changing the due date, right, to Friday or Sunday versus Saturday, how would that affect you? And if you have a strong opinion about it, either way, pro, con, keep it the same, let me know, right? And I'll take all of that into consideration. I hope to see you tomorrow in grass, but if I don't, I'll see you Tuesday. Monday. I keep forgetting we have Monday last. I'll see you Monday.